Good morning. Welcome to Portland. How's everyone today? Out of curiosity, how many people here are also attending DrupalCon? Oh wow, quite a bit. Awesome. So what I'm here to talk to you about today is cryptography. Basically, what that means is, that's a fancy computer science term, but really we're talking about keeping data safe. I have up here a list of 3 things. I'm not going to really read those 3, but there's a couple things I want to make absolutely abundantly clear. Cryptography is not a silver bullet. Everything I'm going to talk about today, you could do perfectly in your application, and if you have another vulnerability in your code, you're still at risk. So really, you need to think security first, and then cryptography later. But security really needs to be part of your day-to-day development practices. It needs to be something that every single developer, anyone who writes code, anyone who designs systems needs to think about security first. It's also, cryptography especially, is one of the most difficult things to do and to get right in programming. And I'll give you an example. This is not confirmed, but we think we may have found a bug in iOS in its encryption systems, because bugs like this are very, very difficult to find, but in any tiny little issue can cause a massive vulnerability. So again, the first rule of cryptography, and this is going to be very prevalent in this talk, and I'm going to say this over and over and over again. I've been criticized for saying this, but I think this is the most important thing for you to understand. Don't do it. If you need cryptography, if you need anything that we're going to talk about here, with the exception of a couple slides, and I'll point that out, hire an expert. There are people out there who do this for a living, who spend 40 hours, 80 hours a week studying this stuff, and who are literal experts, and who can actually implement this stuff safely. If you need this, definitely hire an expert. So, the first thing I really want to talk about, the first piece of actual content, is the foundation for all of cryptography, which are random numbers. When we generate random numbers, there are 3 basic types. There's a weak random number, which are things like you get from mtrand in PHP or the rand function. They look random, but there are problems with it. And we'll talk about some of those problems in a second. There's strong random, which is basically looks random and is actual random. It's very difficult to predict. And the final type is what we call cryptographically secure, which means it's practically impossible for an attacker to predict or to alter or to change. So what are the differences between these 3? Well, we need to talk about 3 types of vulnerabilities that random numbers suffer from. The first one, and the easiest to understand, I think, is bias. So let's imagine we have a random number generator, a function, and we call that function 100 times. It returns us numbers between, let's say, 1 and 10, right? So we would call this number 100 times. We would expect every number from 1 to 10 to appear roughly 10 times, right? Bias says, well, maybe 1 happens 4 times as frequently. So 40% of the time of the output of this function, it's 1. The rest of the time it looks random, it looks pretty decent, but we're biased. An attacker can now use that to be able to try to guess what the next random number is going to be. Because he can say every time, 1's going to be the next number, 1's going to be the next number, and 40% of the time he's going to be right. And when we look at some of the applications coming up, we can kind of see how that's a problem. So the next vulnerability, and if you guys have any questions, please stop me and please ask a question. There's a lot of material and it's builds, everything builds off of each other. So if you don't understand something, please stop me. So the next issue with random numbers is predictability. If I know the past 5 numbers, can I predict the 6th? So to give you an example of this, if I give you 3 random numbers, 3, 1, 4, can anyone tell me what the 4th number is? 1. Why? It's pi. It looks random. the digits are random. If you look at the digits individually, one after the other, they are random. It's not biased because if we run it long enough, all the numbers appear in the same frequency. But the problem is it's predictable. Oh, sorry. The problem is it's predictable. The final one is what we call poisoning. So to understand what poisoning is, computers, the average server that we use, doesn't actually generate real random numbers. What it does is it uses a series of algorithms to kind of fake it. So it keeps this, what we call an entropy pool, or basically a big block of data. And it takes from a whole bunch of different sources. So like in Linux, dev random, the random device, and I'll talk about this in a second, but basically what it does is it gathers data from the computer. It looks at the order in which network packets come in. It looks at clock flutters. It looks at a whole bunch of stuff, keystrokes, how you type, and basically says, this looks like random, so we're going to feed it into this big, gigantic pool. And if we get enough of this random-looking data, we can be sure that the output is going to be random. What poisoning says, the way a poisoning attack works is, it says, well, if I can force that state somehow, if I can somehow manipulate that state as an attacker, I can now control what the random numbers are going to look like on the outside. And this sounds like a very theoretical attack, but PHP's core functions, mtrand and rand, are actually very susceptible to this. And in that case, it's called a seed poisoning attack. So let's look at some functions. In PHP, the way that you can generate weak random data are with these four functions. These four functions are not to be used anywhere that you need security. Absolutely horrible for security. If you see any of these used, at least as a primary source in a security issue, in a security context, massive, massive, massive major problem. So for strong random, we have a couple options. We have Encrypt and OpenSSL random pseudobytes, both of which are extensions. And on Linux, we have dev-urandom. And then for cryptographically secure, so strong random is good for security. Cryptographically secure is good for certain types of security usages. And if you notice, the same functions, the only difference is we got rid of the U. And the reason why OpenSSL pseudobytes is maybe is there's actually a parameter that you pass to the function which tells you if it's secure or not. So never use weak for security, and never use cryptographically secure when not needed. So you remember how I said that there was that pool of entropy? The difference between the strong random and the cryptographically secure is that it keeps track of how many numbers you generate from that pool versus how much input gets into it. So the strong random will constantly let you generate new random numbers. The cryptographically secure prevents you from generating more random numbers than you have random data coming in. So what that means is the cryptographically secure generators will block. So if you try to pull too much data from them, your code is going to stop and wait for it to grab more input, which can take a very long time and can open up other security vulnerabilities, namely denial of service attacks. Okay? If in doubt, from a security standpoint, use strong random. The only real time you're going to need cryptographically secure is when you're generating encryption keys. Things that need to be secure for a long period of time. But most of the time, 99.9% of the time that we face it in the real world, we want to use strong randomness. Any questions on randomness at all? Cool. So the next common misconception, a common misconception that I want to talk to before we get into the next part is encryption versus hashing. Two seemingly simple concepts that are very commonly mixed up. So encryption is an encoding. It's two-way and it's reversible. It's like taking a file, putting it in a box, and locking it with a key. Some point down the road in the future, I can go in with that key and I can unlock the box and get the original document. Another way of looking at it is, I can take you physically, put you in a room, lock the door. I've just encrypted you. No one can see you, no one can talk to you, assuming I take your cell phone. You can't do anything, but I can go and get you back out. Hashing, on the other hand, is a signature. It's one way and it's non-reversible. So it'd be like taking your fingerprint and putting your fingerprint someplace. From your fingerprint, I cannot tell who you are. But if I can get you and your fingerprint, I can say, yes, you are the same person. Make sense? So that's hashing versus encryption. We'll talk in a second about where you would use each. So first, let's dive into encryption. Again, don't do it. So some key terms here. We have a key. In security, in cryptography, a key is a secret, and it is the only secret. Everything else that we do should be public information, and we shouldn't have to rely upon keeping it hidden, except for the key. In reality, it's just a series of bytes or characters. That's what it is physically on the machine, but we call it the key. The plain text is a text you want to keep secret, and the ciphertext is the result of encryption. That's what we send from person A to person B. Or from Alice to Bob, if you've ever read anything. They like to use those two names a lot. I don't know. So there's two basic types of encryption. We have symmetric encryption, which is where we share the same key, and we encrypt our data with that same key. So we have to communicate a key somehow through a back channel. So let's say we're here together, and I want to share something in the future with you. So we decide that we're going to use a specific key today. And then tomorrow, next week when I'm back home and you're back home, I send you some data. Now we can use that key that we both agreed upon in the beginning to encrypt and decrypt that message. Again, lock on a box. Asymmetric encryption uses two keys per person, a private key and a public key. Really, I think the better way of talking about it is the private key is a physical key. That's the thing that you open a lock with. The public key is a lock. So I'm going to encrypt data with my public key, or you're going to encrypt data with my public key. So you're going to put my lock on it, and then now only I can unlock it. So the public key is public. Anybody can know it. The private key is where the security comes in. So it's similar to putting two locks on a box. You put your lock on, I put my lock on. I'm the only one who can unlock mine. You're the only one who can unlock yours. I cannot unlock with your lock. So that's where the security comes with public key authentication. You have those two keys, one of which is always your secret. And they're related mathematically, but that's not overly important for this level of a talk. So let's talk about symmetric encryption, because I find this part fascinating. So let's say we have a number. Actually, it's more interesting if we have a series of numbers. The important thing is that these numbers stand for something. What they stand for right now, we don't necessarily know, but they stand for something. They can be characters, ASCII encoded. They can be temperature readings from a temperature probe. But they stand for something meaningful, and that's the important part. So way back when, probably about 5,000 years ago, some clever people came up with this concept of, let's create a key. This number, we're going to add to every single position in this ciphertext, in our plain text. So we have the plain text up top, we add 10 to each position, and we get the ciphertext in the bottom. Really simple. Really, really, really simple. This is known as the Caesar cipher. If any of you are familiar with that, it's called also rote 13, if you used a fixed number. It's incredibly, incredibly insecure. And the reason is because you remember I said that the original body stood for something? So if it's text, we can do statistical analysis on it. So if you look at a larger piece of text, like a Bible is usually what we talk about, and you look at the letter frequency of individual letters, you can see that E comes up, I'm sorry, not E. Is it E? E is the most frequent. It comes out about 27% of the time, somewhere in that neighborhood. And you can actually, Yeah, no, okay. So you can actually start to look at those numbers and look at the statistical derivation, because if you notice, because we're adding the same number to each position, 10 will come up, 10 in the source will be 10 in the destination every time. So we can start to do, is it? Okay. No, it's okay. Can everyone still hear me here? Oh, okay, I don't need a mic then. I'll be a little harder on my voice, but it's all good. What is that? It's being recorded? Yeah. Oh, okay. So I will turn this on. This is on. Okay. Is it coming through on the mic? Okay. So by looking at a large amount of data, we can now start to statistically analyze and guess. You know what? This number comes up more frequently than all the others. I'm going to assume that's E. This number comes up next most frequently. I'm going to assume that's S. And then by looking at the letter frequencies, you can start to make educated guesses and actually start to guess what the original key was. And the problem with this particular cipher is because it uses the same number in any position, once you guess one letter correctly, you know that key, and hence you know everything. Dangerous. Very, 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 very horribly bad. Not good for security. They've known about the problems with this cipher for 2,000 years. Problem. So how can we improve that? Well, let's add a different number to every position. So we add 10 to the first one, then we pick another number. This right here, this one slide, is the foundation for all of modern cryptography. What differs in all the different things we talk about with symmetric encryption, the difference is going to be how we generate this string right here, that middle string, that middle tier. That's how we adjust security. That's where new things come. But basically, it's about we take a key, or we take something in the middle, and we add it to the plain text. Typically, the addition operator is XOR, exclusive OR, but there are some other ways you can do it, including modulo addition. So basically, we have two fundamental ways we can generate that middle number. The first one is with true random data, or cryptographically secure random data. Now, that can either be incredibly secure or incredibly insecure. If we generate it with random data and we use it multiple times, we have the same problem that we had with before with the Caesar cipher. Because now we can look at, instead of that one position, we can look at that one position in all of the different encrypted documents. If we use it only once, it's known as a one-time pad and is absolutely secure. In fact, it's the only provably secure thing that I'm going to talk about all day. Interesting side note, there is a course on Coursera called Intro to Cryptography, or Cryptography 1 and Cryptography 2. The first homework assignment from that class is taking one-time pads that are used more than once and cracking them. It's difficult until you try it, and then it's ridiculously easy, and you realize how insecure it is. So the other method, the other fundamental method is we generate a random key, that middle part, using a function. Now, it's not truly random because it's generated, but that function is what we call a cipher. A cipher takes two inputs, a secret key and an input, and produces something that looks random. Now, there's different ways that we can combine the cipher, our plain text, and our key. So that's where we get into what are known as modes. There are multiple ways to use that function to encrypt data. Some of them are very secure, some of them are very insecure. So the first one, and the common mistake everybody makes because it's the easiest one to use, is ECB, or electronic code book. Basically, you take the plain text and the key, you feed it into that cipher function, and what you get out is your ciphertext. Simple, and that's why everybody gets it wrong. Effectively, you take a block of plain text, or plain text of fixed length, you cut your plain text by that length, so AES is a 128-bit cipher. meaning every 128 is a block. So you feed in block 1, you get your output. Feed in block 2, you get your output. Block 3, you get your output. The problem is every block uses the same key. So we can actually attack this using similar techniques to the way we attacked that one-time pad. We attacked row 13. It's a little bit more secure than row 13, but not a lot. If you look on tutorials online, you'll see a lot of them have this in their code. Big, big problem. So there are other ways of doing it more secure. I'm going to talk about 2 of them. The first one is called cipher block chaining. It uses an initialization vector, which is not something that's secure. It's not something that's secret. We generate a random number, and that's our initialization vector. We're going to encrypt. We're going to add the initialization vector to the plain text before encrypting it. And then the result becomes the next initialization vector. So we're effectively chaining block 1 to block 2 to block 3. So the key remains the same, but 2 different blocks of plain text that are the same value will encrypt to different outputs. And that's what we want. The next one is called cipher feedback. Basically, very similar, except that the plain text never enters the cipher. And I like this one because basically what it does is we generate a stream of random numbers that we then add to the plain text, very similar to one-time pad. And we never use decrypt because the plain text never enters the cipher. So we take the initialization vector and the key, we run it through our cipher, and then we add it to the plain text. And then we take that block and use it to the next one. Make sense? Easy? So when we talk about ciphers, there's some very secure ones and some very insecure ones. There's a couple points I'd like to make out, especially with PHP. PHP with Encrypt, at least, does not have a cipher called AES. Instead, it has the underlying cipher, which is known as Rindel, or Rindel. I can never pronounce that one right. AES 128 N256, the number refers to the block size. How much of that the key size, how large of a key. The block size is fixed at 128 bits. So when you're looking at a PHP implementation, you want to see Rindel 128. If you see Rindel 256, that's not AES. It's very strong, and actually one interesting thing is everyone assumes bigger is better, right? AES 256 has more known vulnerabilities than AES 128. It's still secure, it's still incredibly secure, but use AES 128 if you have the choice. And there's also some other secure ciphers that are I want to say are non-standard, aren't recognized as a standard. So we've encrypted this data. Now how do we know that someone hasn't tampered with it? We need a way of authenticating that cipher data. So what we do is we create an authentication code. This is where that hash function comes in before. We encrypt our data, then we take a hash of that encryption along with another secret key. So basically, we encrypt, then we authenticate. And then we send the encrypted, authenticated data to the person we want to send that data to. They then can now, with both of those original keys, authenticate that it hasn't been tampered with, and then decrypt it. And the only secret here is the key. So to show you a functioning example of all of this, this will basically encrypt using AES 128, and then to decrypt it, we have the other side. Notice how simple this is. Not really. I didn't do any error checking. Problem. I didn't do any boundary checking, making sure that my inputs were the right type. It's not flexible at all. Everything is hard-coded in here. And how many decisions that I just glossed over. And I said that for a point. This is a fair bit of code, and it's trivial to screw up. So again, don't do it. Use a library. and hire an expert, but use a library. But again, I ask, why do you need encryption? Commonly, if you want to secure data between a client and a server, use SSL. Seriously, guys, just use SSL. That's what it's there for. I find it funny because I'll go on Stack Overflow, obviously, a lot. And you'll see people, well, I need to securely send this between the browser and the client and the server. Okay, use SSL. Oh, I can't. Well, then you can't do it. You can, but just use SSL. That's what it's designed for. It handles all this transparently, and if you're worried about buying a key, there are places where you can get free SSL certificates. And if you're using it to store data, just use full disk encryption. Just use database level encryption. These tools are built and maintained by experts. Don't reinvent the wheel. Use what you have to leverage. And again, really don't do it, but if you have to, Zen Framework 2 has a crypt class, block cipher class, that handles 95% of this magic for you. You set a key on it when you instantiate it, and then you call encrypt and you call decrypt, and it works really, really, really well. There's also PHP seclib, which doesn't require any PHP extensions, but not many others. Yes? There is, okay, so the only legitimate one I've seen, is that my host doesn't allow me to use SSL. And the best answer I can give to that one is, get a new host. Because if your host doesn't let you use SSL, they're probably not secure in the first place. So, I think most of the times I've seen when people can't use SSL or other security techniques, it boils down to their server isn't secure in the first place. So what they're trying to build on top of an insecure platform is always going to be insecure. So beware of tutorials, especially on encryption, because there's not very many out there that are good. Take the Coursera course and then look at tutorials, and you'll understand how to break all this stuff, because that's basically what the Coursera course is. And again, I'm pimping Coursera because it's free. It's, I think, 8 weeks per course, and if you're interested in this, it's really, really fantastic. So the final bit I want to talk about is how do we store passwords, and this is something near and dear to my heart. I do a lot of work with this stuff. So we always want to hash a password. We never want to store it in a reversible format. We want to store the password in a way that we can tell if the user gives me that password, but an attacker can never get the original password out. So we need to use a salt. Now, the concept of a salt is simple. We want to randomize every hash. So we add this little piece of data called a salt that makes two hashes different. Now, this does two things. First, if two users have the same password, it makes the resulting hashes different. And that's good because now someone can't quickly go through the database, find two users with the same salt or the same hash, and now say, that's more than likely the same password, and now I can amortize my attack against that. The second reason is we want to make the attacker have to do more work. If we use a salt, a random salt that's different for every user, they have to attack every single password, every single hash separately, which means they have to do a lot more work, which is what we want. We want to make their lives harder, not easier. So note that because we want the salt to be random, because we want the attacker to have to work, we need that salt to be random across the world. If an attacker finds two hashes on two different sites that use the same salt, they can now attack both of them at the same time. That's why I don't recommend people use usernames or email addresses as the salt. Use a random salt, it's simple. The other thing is that hashes need to be slow. The salt is not enough. And the reason is this thing. Last year, in November timeframe, I believe it was, there was a conference in Norway called Passwords 12. And in it, this guy showed this box and 6 others just like it. It's a 25 GPU cluster. It costs about less than $50,000 to build, and it can do 180 billion MD5s per second. And to put that in perspective, the entire English language, it would take longer to load the dictionary from the disk than it would to execute it. We're talking literally microseconds to do the entire English language. And the leap permutations, turning E into a 3 and all of those fancy things, all possible permutations in less than a second. This is ungodly fast. Your 6-character passwords, which everyone knows are not that secure, 4 seconds. But an 8-character password, which a lot of bank sites have as the largest possible password you can get, in 10 hours per password. That's all possible combinations. This is a game changer. This machine is a game changer. Because prior to this, 8-character passwords were, okay, it's a little bit on the short side, but it's still more than likely secure. With this thing, absolutely insecure when you use MD5. The problem is, MD5 is not that good, right? Everyone knows that. MD5 is broken. Let's use SHA-1 instead. These numbers are remarkably similar for SHA-1. They're remarkably similar for SHA-256. They're remarkably similar for SHA-512. And the reason is because it's not a weakness in the algorithm that this is exploiting. This is exploiting a design consideration. Hash functions, because we use them in cryptography, need to be able to process a lot of data in a very short amount of time. Because we want to sign things, and part of signing is we need the speed. So that all hash functions, SHA-1, SHA-2, SHA-3, Whirlpool, all of those fun things that you see in the hash extension in PHP, they're designed to be fast. That's a primary design consideration. This is the problem with that. So how do we solve this? Well, we want to make things slow. So there's 2 ways that we can make things slow. We can loop a whole bunch of times over a fast function to make it artificially slow. Or we can define a new function that is slow to begin with. And both of them are 100% acceptable. So we have some really good storage algorithms. The first 3, Crypt with Assault basically uses bcrypt under the hood or a couple different other algorithms that are slow, and that's good, that's what we want. PBKDF2 is a standard key derivation function. Don't worry about that. Basically, it takes a hash primitive like MD5 or SHA-256 and loops over it a whole bunch of times in this very particular way, in a way that's designed to be secure. Password_hash, which I'm going to talk about more in a second, is basically a wrapper around crypt. It's designed to make your life easier. You don't have to worry about generating a salt. You don't have to worry about algorithms and error checking and everything. It takes care of all of that for you. And then finally, if you're on older versions of PHP, PasswordLib, which is a library that I maintain, which is designed for interoperability. So it's designed, well, I need a hash password from WordPress and Drupal, and I need to be able to connect to both of them. PasswordLib solved that case for you. And the final one is PHPass. I have screwed up the name of that so many times, I will not do it again. Yeah, I think you can imagine how I would pronounce that. So that's also a good one, especially if you're on older versions of PHP. Everything from this line up, from PasswordLib up, requires 5.3 plus. This bottom one works back to PHP 3. The stuff on top is slightly stronger than the bottom one, but again, if you're stuck on 5.2, well, then again, if you're stuck on PHP 5.2, you need to upgrade in the first place. You have other security vulnerabilities, you have other issues, so just upgrade. But if you absolutely positively can't, you need to, the bottom one is there for you. So let's talk for a second. If you notice, there's a iteration number in PBKDF2. All of these actually take a cost parameter. So we want to target a single password to take somewhere between 1/10 of a second and 1/2 of a second. The longer a single password takes to hash, the better, in general, because that makes the hash harder for an attacker to attack. But we have a problem here. If you have a very, very loaded server, you have a very popular site, and every login takes 1/2 of a second, that adds up very quickly, and that's going to put a lot of strain on your servers. So what I usually say is tune it to your needs, meaning how fast you need your site to be, versus how much hardware and how good of hardware that you have. But think about it for a second. How many times in a session, a day, do you click the login button on a single site? Not that many. Typically 1, maybe 2, maybe 3 if it's a secure site that times you out all the time. If you click on that button and it takes 1/2 a second for you to return, who cares? You're not going to notice it. Your users aren't going to notice it. If it takes a second, your users aren't going to notice it. If it takes 5 seconds, they're definitely going to notice it. But typically, good defaults, good sane defaults, bcrypt is 10, and PBKDF2 is 10,000. But try it on your hardware. Try it and test it and see how it works. So the final thing I want to talk about with password hashing specifically is a new API that is coming out in 5.5. Try it, test it, see how it works, and is also in a compatibility library that I maintain. So basically, there's 4 functions. Password_hash, which takes a password, an algorithm constant, and an optional array of options. It generates a salt for you. It computes the hash, it checks for errors, and it returns you the hashed password. It does everything for you. The goal with this API is to be as simple as possible. Basically, when I designed it, I wanted it to be easier than, or just as easy as someone calling MD5 password. So now the excuse isn't, well, it's complicated and it takes all this code and it's, I don't know how to do it, to, I didn't know that function exists. And once you learn that that function exists, it becomes easy. And that's the whole goal of all of this. So the second function is password_verify, where you pass in a password and a hash, and it says yes or no. Simple. 2 final functions, password_needs_rehash. Basically what that allows you to do is allows you to tune after you have tune the options after you have data in the system. So let's say you started off with cost 10, and then you upgrade your servers and you decide, you know what, I want to upgrade that to cost 11. Okay, you update your cost parameter, or your cost in the options, and then needs rehash will say, yes, something has changed, you need to rehash this password. Gives you a way of identifying if you need to update. And then finally, just a auxiliary informational function, password get info. You pass in the hash, it'll tell you the options that were used to create it. One common thing that I take for granted that I realize a lot of people don't necessarily understand out of the box, the hash that's returned by password hash and by crypt contains the salt. And it contains an identifier to say which algorithm generated it. So that's how the salt gets propagated. You don't need to store the salt. So this is an example implementation of this. When you register the user, you hash the password and you store it. Make sense? Easy? When you log in, you get the hash from the database for that user. You call password verify. If it returns true, check to see if you need to rehash the password. If you do, rehash it and save it. If you don't, just start the session. Simple, straightforward. It abstracts everything away from you. That's the important part here. So some resources on password hashing. The new 5.5 API, and if you want to know why things were done this way, read the RFC. I put as much documentation as I possibly could think of into it. I like to think it's a good read. Now, I'm kind of biased, but. And then the documentation, php.net/password. That's the documentation for the new API. If you're using 5.3.7 or newer, there is an identical replica on GitHub, installable via Packagist, which is a backwards compatibility layer. It uses the same unit tests as the core version does. So you can install that now, use it today, and when you upgrade to 5.5, it'll silently turn itself off, and you'll use the core functions. Finally, password lib and phpass. I always have to be careful when I say that. PHP 4 plus, it's actually PHP 3 plus, so there's an error here in this slide. Make sense? So again, I want to reiterate this point. If you need cryptography, hire an expert. It's well worth the money. You've been warned. Thank you. So, any questions? Yes, in the back. There's a lot of times that you might want to use encryption. I'm trying to think, like if you're going to store data that you need to retrieve that needs to be dealt with separately. I'll give you an example, and actually this is something I probably should have included in the talk. I've included it in other talks. So there's a concept on the internet called a pepper. And some people, non-cryptographers I might add, and that's going to be very, very important later, non-cryptographers have come up and said, you know what, if assault is good, let's add pepper, because pepper's got to be better, right? It sounds so good to be true. And the concept is, what they do is they take a password and they hash it with a secret key that they keep on the server. And they call that the pepper. Then they take the result of that and then they feed that into the salted bcrypt function. So now, if me as an attacker, if I get the resultant hash, I don't have that pepper, and hence I can't really do anything with that hash. I can't attack it. There's a couple problems with that, though. The first one is it's using algorithms in non-standard ways. That's a problem. And the reason that's a problem is because they haven't been studied. We know for a fact that if you take SHA-1 and you feed the result into MD5, the result is significantly less secure than if you had just used one of the two. There's mathematics behind it. It's not straightforward, but we know it to be true because there's actually studies on this. So rather than using functions in ways that they weren't designed for and doing this thing that logically sounds like it should be secure, but we can't tell if it is or we can't prove it is, what I suggest is use something like password hash and then use a block cipher to encrypt the hash. So now you're using these functions in standard ways. You're doing it the way things were designed, and you're encrypting it. So now when you as an attacker download, or when me as an attacker download those hashes through an SQL injection vulnerability, they're encrypted. I don't have the key. I can't do anything with them. And I know I'm secure. So that's one way you can use encryption. There are others, but typically they tend to be one-off use cases. You could use it for encrypting a session cookie. I'd be very wary about that, and I would only deal with open source libraries that do that. I would not implement that on my own because it's difficult to do. It's very difficult to do right, and Ruby on Rails has had vulnerabilities in their session cookies. But those are a couple options on what you would use it for. That would be a legitimate use for not using something else, not using like database field level encryption or anything like that. Correct, correct. Next question? Yeah. Yes and no. So there's an old cipher called DES, Data Encryption Standard. It was the previous standard before AES became standard. It's a notoriously insecure cipher. And it's been around, it's been standard since 1982, 1983, something like that. And it's been known to be broken since 1984. Basically, that's how insecure it is. So because we had all this hardware out there that was built for this DES, they wanted to make it more secure. So what they did is some smart people said, let's make let's take this original algorithm and apply it 3 times. We're going to first take our blocks, our data, we're going to encrypt it. Then we're going to decrypt it using a different key with the same algorithm, and then encrypt it a 3rd time. So by feeding this data through this chain, they actually were able to make DES more secure. And it's called triple DES, or 3 DES. It's more secure, but it's not as secure as using a strong algorithm in the first place. So you can encrypt multiple times, but you have to do it right. Because if you encrypt using 3 different keys, it's actually significantly less secure than encrypt, decrypt, encrypt. Again, minor details that cryptographers, people way smarter than me, can explain why that is. But in general, I'd stick to standard uses. I wouldn't try to make things more secure by, hash all the things. Just sit there and SHA-1 this thing 15 million times. That's not how these algorithms were designed. And I'm very wary about using things in ways that people don't study. So that's how I would answer that. Yeah?
You had mentioned earlier that there was certain methods, I don't know if it was for generating random numbers or encrypting that potentially block.
That what?
That potentially block.
Yes.
Do you have a couple examples of which ones those were?
Dev random. So dev random.
Okay.
So that one. Yeah, this slide, everything on this slide, with the exception of the middle one, will block. So the top one and the bottom one will block if you use it too much. And if you want to try it, get a virtual machine on your laptop and just do cat/dev/random, and it'll generate a whole big block of messy random stuff, but eventually it'll just stop. And then after a couple seconds, you'll see a new character appear, and in another second, you'll see a new character appear. And that's basically just showing you the blocking nature of it. Whereas if you just cat dev u random or dev a random, it'll just go on forever. Next question, over here, there was one. Yeah.
From your perspective, what's the best way to prevent the rising brute force attempts from other application security
Okay.
features that may be available?
So the best way is stop SQL injection, number 1. Make sure that your site is completely safe from SQL injection. Are you not using prepared statements? Go use prepared statements. Stop right now, don't attend the rest of this conference, go update all your applications to use prepared statements. Again, half in jest, half serious. Really, I would focus on the OWASP top 10 vulnerabilities, making sure that you're secure from those. Once all of that is done, then I would start worrying about extra levels of protection. But make sure that the commonly attacked vulnerabilities are there. Make sure you don't have any code exploits. Check to see, are you using eval? Are you using create function? Things like that. General web security best practices, that's what I would go for. Yeah?
What strategy would you suggest for places where secrets are no longer stored in a secret fashion? So a JavaScript-based API for mobile clients.
What kind of secrets would you be storing?
Well, I guess Twitter famously recently they got their API keys taken out of their clients on all the platforms, and they obviously don't have any way around
Right.
keeping those keys in their clients.
So there's actually, and this is topical, I just read today, there's a draft RFC around by IETF, Internet Engineering Task Force, for securely communicating keys using passwords. So basically now what that'll allow you to do is a handshake at the start of a protocol. So you have a REST API, you do a handshake before you start with that REST API, which gives you a secret for that session. And that's the only validity of that secret. So then now after your session is over, or after a predetermined amount of time, that secret's no longer good and you need to re-authenticate and renegotiate. That's basically how I would have to handle that. If you need anything more than that, you're going to have to generate a new secret every time on the client and then register it with the servers, preferably through a back channel. Things like that are difficult, and that's also, I have this slide here so many times. The reason is storing secrets is hard. Storing secrets is hard. Say it with me. Storing secrets is hard. No. It really is hard because the best way to store a secret key is also one of the most expensive and difficult ways, which is off of the server. For encryption specifically, there's hardware modules that you can get which store an encryption key inside of the circuitry of the module. So as an attacker, if I can gain root access to the device, I still can't get the secret key. That's the best way of handling secrets, is at the hardware level. Make it so that the operating system can't get it. All it can do is ask to encrypt or decrypt data. It can't actually get to the key. There's actually a lot of different ways to do that. One way, and I use these things for password storage, is the YubiKey. Basically, it's a one-time pad. It has cryptographic secrets on it, and it creates a new derived key every time that you press the button. It appears as a USB keyboard when you plug it in, but it never actually leaks the secret key. So unless someone physically gets this device, if you intercept one of mine, you can never know the rest of them. And that's, I think, the better way of handling it is generating and deriving keys from a secret that cannot be accessed. But again, that's why I hire an expert, because it's hard. Yep.
Yeah, you were saying that we should randomize our salts.
Yep.
Did you say there were ways that we shouldn't be doing it? So, how do we randomize our salts? So we make sure that
Okay. We don't need to make sure that they're 100% guaranteed to be unique. All we care about is statistical uniqueness. And to put this in a context, if we generate a 8-character salt, and we use a decently strong random number generator to do that, you have better chances of winning the lottery 10 times in a row than you do of having 2 of those collide. So when I say they need to be unique, I'm talking they need to be statistically unique. Generate a big enough salt where the chances of 2 hashes having the same salt are low enough that we can just not worry about it. You don't need to check your database every time you generate a salt to say, did I use the salt? Did I use the salt? You generate it with a strong random number generator and you'll be fine. That's how PHP, that's how all of these do it. All of these abstract it away from you. The way I'll phrase it is this. If your code is generating a salt, you're probably doing it wrong. Use a library. Let a library generate it for you. They're maintained by smart people. So why not use a library? Any other questions? Oh, yeah, one more, and that's it. Dev urand, it actually uses 3 methods. All right, wait. The core one uses dev-urandom in all cases. And then if it can't generate as much data because some hardware configuration issue, it will fall back to using rand, but it does it it tries to do it in the most secure way possible. And password compat will use mcrypt, OpenSSL, or dev-urandom, as well as using mtrand to fill in the dots. So it tries to use a number of different techniques. And one other note on random, if you need random number generators, I also maintain a library called randomlib, which abstracts all of that away from you as well. So you can just generate random data, and it uses standard compliant ways of generating random data. So that's basically how I'd answer that. Thank you very much. One request, go to this website, joined.in, and rate all of your talks. As speakers, we need your feedback. So please, after every single talk, please go in on Joined In and rate the talks. Thank you.